Hello, everyone. Welcome to Recitation 3 on Mechanics and Materials 1. In this recitation also we have 4 questions. Please feel free to interrupt me if you have any question, because I'm looking down, obviously, because I'm writing down. But please feel free to interrupt me if something is not clear or you have a question. All right. So the first assignment here is the following. You are given the plane as shown here in the picture. And for this plane, you are asked to compute the coordinates of the centroid. So it's a purely geometrical problem. It's not really complicated. You have 2 ways of doing this. Either you look into the tables, so you assume that you have the tables in the book and you just use them, or you can use an analytical formula, or basically you can just calculate it via integration. I'm going to show you both. So the first way of doing it is just to think about it as 2 surfaces. So you would have this upper area and you have the lower area. Now, for each of them, you have a formula from the book. So you know, if you have a parabola like this, let's say if this side is A and the height is H, then the coordinates for the centroid are such that here you get 3/4 of A, and in the y direction you get 3/10 of height. Okay. Also, the area of this thing. So again, if it was a rectangle, it would be 1/2 of A times H, but the area of this is 1/3 of A times H. Okay. So you know this from the tables, so you know where this point is. So if we call this, let's say, area 2, and we call this area 1, and you know also where this point is. So for each of them, you know exactly the coordinate. The lower one obviously is a rectangle, so rectangles are standards. You can just use the one you know. So what you want to do is basically to use our formula. So we know x bar, that is the unknown we are looking for, times sum of the area, or the total area, is equal sum of the xi ai. Okay, so this one, the total area or area sum, is simply area 1 plus area 2. What are these? Area 1 is 15 times 80. So this is the area of the rectangle. Area 2 is 1/3 of 50 times 80. So again, this would be A2. And if you compute this, the total area would be, well, I'm going to actually spell it out. This is 1200 plus 1333.3 if you want. So this is 2503.3. So this is the total area, and then you just need the coordinates. So now you know x bar is, let's say in this case, x1 a1 plus x2 a2 divided by that total area, which at this point we know it's 2533.3. We also know what is A1 and what is A2 already. So all you need to know now is X1 and X2. x1, assuming that this is, let's say, your coordinate system, right? x1 would be the distance, the x distance of the area 1, or of the portion 1, and that is obviously 40. x2 is the same thing for area 2. So it's this distance, which we just said. It has a formula. So x2 itself is 60 millimeters. So it's 3/4 of 80, which is 60. So you just insert these, and you end up with x bar equals 50.5 millimeters. All right? I am a little sloppy about the dimensions and units. Everything is in millimeters. The areas are millimeters squared. So I don't keep repeating them, but you get the idea. All right, so this is for the x coordinate. For the y coordinate, basically we do the same thing. So it would be y1, a1, plus y2, a2, divided by a total again. So again, we know what is a total. That's no problem there. A1 and a2 are fine. We just need y1 and y2. So if you look at here, now y1 is half of the height that you have here. So that would be 7.5. But for y2, pay attention that you need to add this distance, so this one, also to the distance that you get from the formula. Okay? So from the formula, you know it's 3/10 of the height. So let's say this is 50. 3/10 of that, that is 15. So that tells you this height here, that is 15. But you also add that with this 15, so the distance from, let's say, from the x-axis would be 30 altogether. So it's 15 plus 15. Okay, so as I mentioned just now, y2 is just 3/10 of 50 plus that 15 that we had at the bottom. So that would be 30. And y1 is half of 15, which is 7.5. So if you do that, you get also y bar, which is 19.34 millimeters. Again, if you just look at the, let's say, the coordinates and the picture, they make sense. So you can imagine that the center of the whole thing, it should be on a line here, which is on the right-hand side of 40 and on the left-hand side of, let's say, this one, the 60. So you expect to get something which is between 40 and 60, so you get 50-something. And then for the y-axis, obviously you expect it to be above the, above this one. So, all right. Do you have any question? So this was the first way of doing this. Here we just use the, let's say, the formula that you have in the tables. What I want to do next is to come to the same example and try to use the analytical formula for that. So basically integrate that. Okay, so if you think about the curve that we have here, you can write this curve as just f of x. And it's a quadratic curve. You know it's a parabola. So if you want to find the equation for that, you can start from your usual generic equation, x squared plus bx, let's say, plus c. And then all you have to do is to insert the coordinates of 3 points. But you only have the coordinates of 2 points. So you need a third condition here. The third condition is that you know it's becoming flat here. So let's say if this is point A and this is point B, you know that at point A, this equation holds. So if you put the coordinates of point A, this holds. If you put point B, this one also holds. So that's your equation 2. The third equation is that the derivative of that function at A is 0. The derivative of that function is 2 small a x of A plus B equals 0. Okay? Now, these are 3 equations, 3 unknowns, and from that you can calculate or you can find out the equation of the line. If you do that, so here, for instance, okay, let me just put this. This is capital A. This is point A. So point A, the coordinates of point A is 0 and 15. Coordinates of point B is 80 and 65. So if you insert that, for instance, here in this equation, if you put xa, this term will vanish, so you know immediately that B is 0. Okay, B is 0. It tells you that this part is 0. So you expect your equation immediately to be like this, which you may know already from, let's say, other methods. And then if you use the coordinates of points A and B in the y equation itself, you can calculate A and C, the coefficients. C will be 15, which you can immediately see y if you just insert coordinates of A here or here. C becomes 15, and A would become 1 over 128. So essentially, the curve, the green curve, has the relationship or the equation 1 over 128 x squared plus 15. So once you have that, now you can just integrate it. So if you integrate it like you usually do, the area would be integral of y dx from, let's say, 0 to 80 of x. So you can do that. So area would be integral of, let's say, y dx from 0 to 80. And that gives you integral of that 128 x squared plus 15, let's say, dx from 0 to 80. And that gives you 1/3 of 128 x cubed plus 15x. It goes from 0 to 80. And obviously, at 0, all of this disappears. At x equals 80, you get the answer for the area. And if everything is correct, that gives 2,533.3. Okay, so you get the area. Now, for instance, you want x bar. So you can do the same thing. So you would say x bar is integral of x dA, again, from 0 to 80, divided by integral of dA, which is a. And at this point, we just calculated it, so we know what that is. Now, for the denominator itself, this thing becomes integral of 0 to 80 of x. Instead of dA, we would say y dx. So this thing itself is just dA. And y is the function that you just have here, right? So you just insert that. You would say this is integral from 0 to 80, 1 over 128 x cubed plus 15 x dx. And then you integrate this up, obviously. You get 1 over 4, 1 over 128 x to the power 4 plus 1 over 2, 15 x squared from 0 to 80. Again, at 0, everything disappears. And then if you have done everything correctly, you get something like 128,000. And if you divide that by 2,533, you get x bar, which is something like 50.5 again. All right? So this works, the integral. Do you have any question? So again, there are two ways of doing this. You can do it either way. Obviously, using tables are easier. And if we ask you for something like this, we usually give you the function itself. But if it is quadratic, obviously, or constant, using tables are recommended. You have a question? All right. Okay, so the next assignment is very similar to that, except that it is a little also mixed with mechanics, let's say. So we have a beam supported at point A. So basically it means you have a beam like this. And at point A, it's fully supported. It's a fixed support, it's clamped. That means you would have two directions of a force at point A, AX and AY, and you get a moment MA, and then again, I write it, or I draw it as if it is counterclockwise to be plus or positive. Now, on this beam, you have the distributed load as shown here. What you want to do is exactly the same thing. In order to calculate these reactions at the support, that is what you are asked to do, you need to replace this distributed force by individual forces. Okay? Now, in order to do that, we pay attention that it's a parabola. Again, if you had the function, you could just start integrating and it would be fine. But since we don't have the function, maybe it tells you that you should use the, let's say, the formula in the books or the tables, but you can see that your parabola ends here. So we have a little problem with the way it is constructed. So what we want to do is to split it into two parts. You basically shift it up to get this orange distribution. You shift everything up, and then you add this much, the 300, which is this little part that you have here, in the opposite direction. Okay? Now, if you add this together, so these are upwards, by the way. And this is a constant, so this is a constant rectangle, and this is your parabola. Now, if you look at this picture, this makes perfect sense, because now for the parabola itself, you can replace it with a force R2, let's say. So let's call this again, let's say area 2 maybe, and we call this area 1. So you can replace this by R2 effectively, and you can replace the rectangle by R1. Now, R1 for the rectangle is the area of the rectangle. The area is 6 times 300, which is 1800. And you can imagine the distance is half of 6, which is 3. For R2, the area is 2/3 of 6 times 900. Sorry, 2/3 of 6 times 1200. Remember, this was 900, and we added 300 to it. So the whole thing here is 1200, and we want to compute this area, right? So you would have 1200, 6 is this, and 2/3 is the coefficient for the area under parabola. Please pay attention that if you think of a parabolic function like this, you can think of two areas, right? I mean, there is this area and there is this area. So if this is A and this is H, this one is 2/3 of AH, and this one is 1/3 of AH. Okay, so it depends which area you are talking about or which way your parabola is turning. In the previous problem, we had 1/3 because we were interested in this area. But now we are interested in the other one, so there is a 2/3. All right, so we do that, and this gives you 4,800. And the distance of that is 5/8 of the length, in this case 6, and that would be, let's say, well, it's 30 divided by 8, which is 15 divided by 4. Okay, so now you know what are these two forces and where they are applied. So you have a R1 here, and you know it is applied at the distance 3, and you know it is 1800. You have a R2 here. By the way, you see R2 is downwards, R1 is upwards. It's because of the way we constructed them. And this one is 4,800, and the distance here is 15 divided by 4. All right, so this is the picture we want to now solve. So all you have to do is to write your equilibrium of moment with respect to A, or start with forces, it doesn't matter. You can do it either way. So let's say if you write equilibrium of moment with respect to A, assuming that counterclockwise is positive, you see R1 is upward, so if you multiply it by this distance, it would be a counterclockwise moment. This one is downwards. If you multiply it by this distance, that would be a clockwise moment. So this one comes with a plus sign, this one comes with a minus sign, and this one itself is a plus. So you would have MA itself plus 3 times 1800 minus 15 divided by 4 times 4,800 equals 0. And that gives you MA equals 12.6 kilonewton meter, or 12,600 Newton meter. Just a little remark here to be careful. You see here I'm writing sum of moments with respect to A is 0. So MA 0, and then here I say MA is something. There is a little detail here, and this is because of the way that we write this equation. So when you write this, I am talking about the sum of the moments with respect to point A, okay? So this is sum of moments with respect to point A. With respect to A. But when I'm writing this one, I actually mean moment at A. At A. Does that make sense? So the sum of the moment with respect to point A, it also includes the moment at A itself. So it would have been more correct if, if here you actually write with respect to A, and here you write at A. They are not the same thing, obviously, but since it would get really crowded, and we usually know exactly what you mean, we can just write it like this. So if we write M with respect to A, whether it comes as a sum with respect to or just moment at, I don't mind. You have a question? The support. So here the support is a fixed support, right? So this is not a hinge. So if it was a hinge like this, the hinges can only carry two forces, right? But we have a fixed support. And again, I remember we had this example. It's like you have a pen in your hand and you just push it in, right? Then you cannot turn it. It's exactly like that. So this thing is a fixed support or clamped. Not hinge. All right, from the shape, or from the drawing, actually, you should guess. But yeah, that's that. All right, so we have now the moment at A. So the next thing you want to do is, let's say, to calculate the forces. So you can say the sum of the forces in X direction is 0, and sum of the forces in the Y direction is 0, assuming upward is positive. So here you would have only one force in the X direction. So that's AX, 0. In the Y direction, you have AY upwards, plus 1800, again, upwards, minus 4800, that's downwards. This is the R2. This thing must be 0, so that gives you AY equals 3000 newton. Okay, so that's your problem 2. Yes?
I couldn't understand how they change the shape into a parabola and a rectangle.
So did you understand it for this example, like we split it? It's exactly the same thing, except that it's the backward process. So if you look at this shape, you see it's very similar to what we had. There is a rectangle at the bottom, and there is a parabola on top. And remember, we split them into two parts to calculate that?
Yeah, but I didn't understand, like, at the bottom rectangle, how can it be, like, equal to the parabola's, like, little piece?
Okay, why we did. Okay, maybe let me just. So here you have a line. Okay, and let's draw a different. I want to just draw the previous example so that it doesn't look similar to this. So think about the parabola being like this. Okay, like the example that we had previously. So if this was the example that we had previously, and you know that the forces here are downwards, and the forces here are upwards. So see, there is a change of, okay, maybe I should duplicate it and clean it for you to see. So you see, the problem with this is that this is not a geometrical shape. This proportion, so this one is upwards, and this one is downwards. Okay, you didn't, by the way, you didn't have to do what I just did. You absolutely do not have to do that. You can do the following. You can just say, well, for this part, I am going to calculate the effective force. Okay, and for this part, I am also going to calculate the effective force. Let's say you call this F1 and you call this F2. This would have worked. So this would have perfectly worked. But then F2 would be up to this point and F1 would be up to this point. Does that make sense? Okay, so you could have done this. But if you wanted to do this, maybe you can see it's a little complicated, because then you deal with these two parabolas and you need to find out this point and so on, right? So it has that little complexity. You need to find out where this point is, where it becomes 0. And then if you have that dimension, of course, let's say this would be A and this would be B, and you know A plus B would be 6. and you can calculate it. So you can do it like there are two portions. Okay, but it's much easier if you just, let's say I am going to apply or add a constant force upwards to the whole thing. So if you just add consistently 300 upwards everywhere, what happens is that you get that 300 that you just applied, so you pushed up everything, and then you get a nice parabola which the zero starts at 0, and then we know how to handle that much easier. Does that make sense? So it's just for the convenience, otherwise this would have worked equally. Do you have any question? All right. By the way, since we just discussed this in a related note, this is something, we will see actually an example here very soon. So if you have a picture like this or a loading like this, we usually split it into these two parts. But there is no reason you need to do that. For instance, you could have just done it like this. You know, if you wanted to, you could just do more triangles. Or sometimes, let's say you have a longer portion at the bottom, you could even do this. So you can have one triangle here, and then, I don't know, another triangle here. And so there is no one single way of doing this. It really comes down to your taste. Okay, so thank you for the question. Do you have any other question? All right, so the next example is very similar. Now, we have a beam. It has these two portions of forces. What you want to do is to compute the reaction at the support such that it's minimum with respect to the distance a here. Okay, so let's say mathematically, if this force here is By, we want to compute that By as a function of the distance a, and we want to minimize that with respect to that, which means we want to set that derivative with respect to a to 0. Okay, so this is a very, very simple problem, actually, now that you look at it. You have three unknowns, ax, ay, by, and you have these simple loads or loading conditions. They are just triangles. They are simple. So all you have to do is to replace them by two forces, equivalent forces. So I'm going to, for instance, put this as R1, and I'm going to call this one R2. And let's say the distance for R1, if we call that X1, and the distance for R2, you call it X2, you can calculate all of this just from the triangles, right? So for instance, here you can immediately see that X1 is 1/3 of A, right? And X2 is eight plus A divided by 3. You don't see it immediately, but you can calculate it again similarly. So you can basically add this distance to A, and you will see that. All right, and the amount of them, obviously, so R1 is the area of this little triangle, which is 1800 times A times 1/2. R2 is the area of the right triangle, which is 4 minus A, well, 1/2 times 600. Okay, so this is the area of the right one, that's the area of the left one, and now all you have to do is to write the equilibrium with respect to, or equilibrium of moment with respect to A, to get By. So again, we write equilibrium with respect to A because we want By as a function of A. We are not at this point interested in A, X, and Y, so we know this is the best equation. Also, at point A, you have a hinge. So a hinge does not apply any moment. So the moment of the support A itself is 0. So you only get a moment from R1 and R2 and B. Now, if you look at this, R1 is downwards. So it's going to cause a clockwise moment. R2 is also downwards, so that also causes a clockwise moment. By is upwards, so if you multiply by this distance, that will cause a counterclockwise moment. So that comes with a plus, these ones come with a minus. So basically what you get here is 4 times by. This is the plus, because it's counterclockwise, minus, okay, let me just write it like this. R1 times x1 minus R2 times x2 is 0. You insert R1, R2, and all that, and you get by to be a function of a. That would be 50a squared minus 300a plus 800. Now, derivative of by with respect to a, if you want to set it to 0, you can immediately see it gives you 100a minus 100, that is 0. So that gives you a equals 1. So if you insert a equals 1, then by would be 750 Newton. Then you can write equilibrium of forces in the y direction. And then again, if you assume upward is positive, you would get by, which is plus ay, that's also upwards, minus r1 minus r2, because both of them are downwards, that is 0. So now you know these ones. So ay would be 1050 Newton, and then you write equilibrium of forces with respect to x direction, and that just gives you ax is 0 because there is no other horizontal force. All right, so that's that. Do you have any question? Okay, so the next exercise is this one. It's very similar to the exercises we had. There is only a little bit of geometry involved in this, so I'm going to explain that part of it. So you have basically a water tank like this, and then there is a gate here. At point B, this is frictionless, meaning that you don't get a force in this direction. So in this direction, there is no force from B. So all the force from B is orthogonal, like that. So you would get, let's say, a force from B here. This is your force at B. Now, from the cable, you get a tension there. So this is your tension then. This is the tension from the cable. And at point A, obviously, you would get your usual AX, AY components. So what you want to know is how much. So this is the problem, by the way. So you are pulling this cable, and you want to know how much you need to pull such that it starts to open, the gate starts to open. You can imagine, if you don't pull it at all, there is a water pressure, so it keeps the gate shut. So you need a certain amount of force to make it open. In that moment, in that instance that it starts to open, that means you have equilibrium, right? So it means the amount of T that you apply is exactly the same as you need to compensate for the pressure that you get at that. So what you want to do is to write equilibrium, okay? So now equilibrium, again, it's equilibrium of forces and moments. We are interested in T. We are not interested in AX and AY. So we are going to write the equilibrium of moments with respect to A. Again, assuming that counterclockwise is plus. This is the easiest, right? So if you do that, you get basically two forces in the picture. One of them is the moment that you get from T, and one of them is the moment that you get from the pressure. So let's say we assume the pressure is applied here. So this is the effective force from the whole pressure in the tank. And the distance is D. And by the way, the angle here is orthogonal, or is 90 degrees, because you know from pressure you always get normal force, right? So the effective force from the pressure is already that. Now, if I knew the distance here, let's call this distance maybe A. Okay, small letter A. Then the equation you want to solve basically is this, that T times A. So T times A, you see T is now orthogonal, so T times A would cause a clockwise distance, a clockwise moment. And then D times F, it will cause a counterclockwise moment. So this comes with a plus, is 0. All right. So all you need to compute in order to compute T is A, F, and D. So we need to find out these three, and then we can calculate T. Does that make sense? So A itself is very simple. You can get A from, let's say, from the geometry. So if you look at this angle here, and you call this angle, I don't know, what did we call it? Let's say we call this theta. If you multiply this distance times the sinus of theta, you get A. All right? You can do that, or if you call this angle alpha, you can do the same thing here. So you can say AB times sinus alpha. So what I'm trying to say is that if you want to construct A, it's either AB times sinus alpha. Okay, so AB is this. You have this angle. So this will be AB times sinus alpha. Or you look at this triangle. That would be, let's say, AC times sinus theta. Okay, now you know exactly what AC is anyway. This is 0.45 plus 0.27. You also know what is AB, by the way. It's 0.8. Okay, so maybe you don't see exactly the AB. Let me just tell you why it is 0.8. So if you draw this triangle, if you look at this triangle, you see, you have 48 here, 64 here. So if you divide this by 16, this is like a 4, this is like a 3. So this would be like a 5. You remember there is this standard triangle, right? So if you think of this standard 3, 4, 5 triangle, this would be your 0.48. This is your 0.64. So this would be 0.8. Okay, so that's why AB is 0.8. All right? So the only thing you need to know are the angles theta or alpha. And then again, if you look at theta, it's easy. So you have the tangent of theta. So basically, you can also construct theta itself. So tangent of theta is 0.64 divided by, let's say, everything that you have on the side, so 0.27 plus 0.45 plus 0.48. But also you can, again, think about this one and simply construct sinus of theta, because you know later you need sinus of theta. So if you do that, that also works because, again, you know all the distances, so you actually know BC will be 1.36. Okay, I'm going to, so if you look at this triangle here, this is 0.64, this is 1.2. Okay, so again, you can calculate BC. So again, this is a standard triangle. You have 0.64 here. You have 1.2 here. So from this, you know BC is going to be 1. Okay, A is somewhere here, but we don't care. All right, so basically, if you know BC, you know sinus of theta is 0.64 divided by 1.36. So sinus of theta is 8/17. All right, so my point being, A is AC times sinus theta. You know what is sinus theta, you know what is AC. That's fine. So we have one unknown less. So A is equal 0.45 plus 0.27, which is AC times sine theta, which is 8/70. Yes?
Is the C point is fixed?
Yes. It's a pulley, basically.
But is it fixed like it's not connected to, the BAC?
These are all, so this is one rigid element altogether.
That C can move too.
C can rotate.
This road.
Yeah, it's a pulley. So it's like this. The point in the center is C. Okay, so this is point C. And this is your cable on top of it. Does that make sense? Assume the pulley is very small, if that's why you are asking. So the radius of the pulley is not too important right now.
That's not why I asked, because like the AC going to move from B, right, to upwards. But it has to rotate from some point. Is it going to rotate from A, or is it going to rotate from C? Is it like a BAC?
Oh, no. Okay, thank you. No, nothing rotates. Nothing. So assume this is a wall here. Okay, so this part is not moving. This is attached to a wall. Okay, nothing moves. Okay, so the whole thing is a static problem. There is no rotation or change of the geometry. All right, so this was the more difficult part of this problem. Now, the rest of this is simply to look into the pressure distribution. Now, if you look at this problem, you know the pressure is always normal, or it causes a normal force. So you would have a normal force here, which is, let's say, rho GH times A being the area of this, which is the length of it times the thickness, in plane thickness of it, and H is the height from top. Okay? Now, you have that much, like a constant, and then you have a changing part. So if you look at your AB, so let's say if this is your AB, you would have a pressure which has a constant part and it has an increasing part. Okay? So this part would be rho GH, which is 0.45. And this part would be rho G 0.48. Okay, so from the first part, you get an equivalent force. From the second part, you also get one, and you just add them together. So at this point, all you have to do is, I mean, maybe you can turn it so that it becomes more familiar to you. Now, it's basically this problem. You will replace the force from the triangle by just a single force. You get also a force from the rectangle. So the force from the rectangle is the area of the rectangle. And you know, the distance here is just AB, right? So the drawing that I had, it was A, this was B. And you know AB is 0.8. So this is 0.8. Okay, so basically this tells you that FR is 0.8 times rho G 0.45 times, there is a 0.5 because also there is an in-plane thickness, so there is a third direction to this, which the problem has given us. Okay, it's this. Okay, so that is FR, which happens to be 0.18 rho G, and it acts at 0.4 from A. So the distance here for FR obviously is 0.4, right? It's a rectangle, so it's in the center. It's half of 0.8. Then you have FT. FT would be the area of the triangle, so 1/2 of 0.8. Now rho G times 0.48. Again, that 0.5 because of the thickness, and that you get 0.096 rho G, which acts at 2/3 from A. 2/3 of 8. 2/3 of 0.8 from A, right? So you know where that one acts. And now that you know all this information, all you need to do is to replace it with a single force. So what you want to do is to basically find this equivalent force, which is basically FR plus FT. And all you need to do is the distance from A, which is D, okay? This D is exactly the same D which we defined here. This is the one that we didn't know. Okay, so F itself is FR plus FT. D is that effective distance. So all you have to do is to basically treat it like you usually do. So D would be 0.4 times FR plus 2/3 of 0.8 times FT. This is the effective force times distance, or effective moment, and divided by the sum of the forces, that's FR plus FT. And if you do that, and you insert the values from there, you would get D equals 0.4464. Okay? Now you have everything. You remember the relations that we wanted to have is up here. So this is basically FD equals TA. Now you know what is D. You know what is F. So F is the sum of FR plus FT, which we also know. And you also know what is A, which we had it up here. And if you insert those, you would end up with T being 3,570 almost. All right, that's it. Do you have any question? By the way, just for the fun of it, if you wanted to calculate these angles, let me just, because you could also do it through different triangles in this example, but if you wanted to, this angle alpha, if you calculated it, it would have been 25 degree, and this other angle, if you wanted to, it would have been 36.87. So you could have done slightly differently. Again, yeah, that's it. All right, do you have any question? Okay, thank you very much. So this was the last question for today's recitation.